Hello students, you are welcome to AAE 468 Advanced Orbital Mechanics Astrodynamics video lecture. Today is what's today's date? Today is the 12th of February 2015 and the time is 11 minutes past 10. Like I said in the previous video lecture, this is going to be more of me making a video of how I prepare, or me making the slides which I'll be sending to you. Actually, this first slide that we are on, you have a copy of it, and I'm just going to be updating it. When I've updated it, I'll be sending it to you, hopefully with the videos that I'm making while I'm making the slides. And I hope you understand why it has to be this way. Because of my own tight schedule here, I don't have much time to read well and prepare well before making the video lecture. So I'm kind of like putting the two together, the reading and preparation, which of course I have to do for the class, and then the video all together. So please bear with me. So in the previous video, I started with all this, and then we got to we looked at the concept of the celestial sphere, the right ascension, the declination of a body as viewed, a body in space as viewed on the celestial sphere. Look at all that, and then we said if we have the state vector, we could calculate for if we have the state vector, we calculated for, let me just try to refresh my memory here. Yes, so given the state vector, we calculated for the right ascension and then the declination of such a body. What I meant to say is, given the state vector of, let's say, a satellite, we saw how we could calculate for its right ascension and then its declination. So now we are going to move forward and go on to the orbital element and the state vector. And I think I've already put this on the slide somewhere. Yes. And since the textbook has done quite much in explaining all this, I've just been snipping relevant portions of the textbook, which I think brings out the actual things that you want to learn, and then putting them on the site. Occasionally, I might also be putting some form of explanation, which are in my own words. So let's just move on. So now we'll be looking at orbital elements and the state vectors. So to define an orbit in the plane requires two parameters: eccentricity and angular momentum. Yes, if you recall the orbit equation, R equals h squared over mu times 1 plus E cos theta, where theta is a true anomaly, h is the specific angular momentum, and then mu is the gravitational parameter. So, of course, to define the orbit, we just needed the specific angular momentum and then the eccentricity of the orbit. We noted then that the eccentricity could vary from zero. If the eccentricity is 0, you know it's a circular orbit. If it is in between 0 and 1, you know it's elliptic. If it is greater than equal to 1, you know it's parabolic. If it is greater than 1, you know it's hyperbolic. So given the angular momentum, specific angular momentum, and then the eccentricity, you were able to say something about the orbit. You were able to say it's an elliptical orbit. If this is the case, you're able to say it's a circular orbit if the eccentricity is equal to 0. And you could say it's a parabolic trajectory if eccentricity equals 1, or it is hyperbolic trajectory if eccentricity is greater than 1. So to locate a point on this orbit, let's say this is the major gravitating body in the two-body system, and this is the second body. So to locate any point on this orbit, then we need the knowledge of the true anomaly, theta. So with the specific angular momentum and then the eccentricity, we are able to define what kind of an orbit we are talking about. And then to be able to pinpoint some points on the orbit, you need the specification of the true anomaly, theta. So that is what this paragraph is talking about. So to locate a point on the orbit requires a third parameter, the true anomaly, which leads us to the time since perigee. So in order to be able to locate the points, we needed to also, and we saw this from AAE 313, we needed to have an idea of the time since perigee. That means if we know the time that the satellite passed through the perigee, we could we could now try to calculate the time, and it has moved past the perigee, so we could try to calculate the time it has spent since it passed through the perigee. And the perigee, of course, is its closest approach to the major gravitating body in the two-body system, which, of course, is the Earth in this case. So we go on. Describing the orientation of an orbit in 3 dimensions requires 3 additional parameters called the Euler angles, which are illustrated in figure 4.17. So the figure is a bit confusing as it is now, but as we go through the rest of the slides and the text, I'll try to be making explanations on this part of this screen. So first we look at the intersection of the orbital plane with the equatorial XY plane. So the equatorial XY plane is that shaded plane there. So if I just switch here. So let me start by drawing the equatorial XY plane. So as the equatorial XY plane, and then I'm just going to add the XY axis. So that is X. And you know it's an inertial frame of reference because we define that to be an inertial frame of reference. And that is Z. So we need to find the intersection of the orbit with the equatorial XY plane. So let's say the satellite is going in an elliptical orbit in such a manner around the Earth. So of course the Earth is, let me just try to sketch it. So that's the Earth, and the satellite is going in an elliptical orbit around it in such a manner. So what we need to do now is to first locate the intersection, that point, the intersection of the orbit, the orbital plane, with the equatorial plane of the Earth. So this point, that point there, that's the point that we are talking about now. So first we locate the intersection of the orbital plane with the equatorial XY plane. That line is called the node line. So the line which passes through the point which I've just illustrated to you, this point here, is the node line. So the line that passes through it is a node line. The point on the node line where the orbit passes above the equatorial plane from below it is called the ascending node. So let's say the satellite is coming in this manner, going towards the node line in such manner. So when it goes, coming from right beneath it and going upwards like that, that point is called the ascending node. And of course, the other side of the or the other place where it's going to intersect with the equatorial plane, or the next time it's going to intersect with the equatorial plane, it's going to be going from upwards downwards. So that other point is called the descending node. So the descending node. The node line vector n extends outwards from the origin through the ascending node, as you see there. At the other end of the node line, where the orbit dives below the equatorial plane, I've just tried to explain, is the descending node. The angle between the positive x-axis and the node line is the first order angle, and it is capital angle gamma. Sorry, omega. This is omega, capital omega. And it is the right ascension of the ascending node. Yes, the right ascension. That means the angle between the equatorial x-axis and then the node line. That is the right ascension of the ascending node. Yeah, you call that the right ascension is a positive number lying between 0 degrees and 360 degrees. The dihedral angle between the orbital plane and the equatorial plane is the inclination. So this angle here, this angle here, that's the angle we're talking about. So that is I, the inclination. So if I just try to draw the node line, make it like this. Is it coming from the origin? Yeah. So like that, that's the node line. And then this angle here, that is omega, and then it's the right ascension of the ascending node. So that means the satellite is going in that manner, going in that direction. So the inclination of the orbital plane to the equatorial plane, of course, is called the inclination. It's denoted by I. So it is measured according to the right-hand rule, that is counterclockwise around the node line. So like this, counterclockwise, you see, that is the node line. That is the node line there, and this is my right hand. So this is a positive sense of I. So my thumb is pointing in the direction of the node line, and then this is a positive direction. That means from the equatorial plane up to the orbital plane. The inclination is also the angle between the positive z-axis and the normal to the orbital plane. So because the orbital plane is inclined to the equatorial plane, of course, the normal to the orbital plane, which is where the specific angular momentum vector resides, is also going to be inclined to the z-axis. The z-axis, which is normal to the equatorial plane. So because the orbital plane is inclined to the equatorial plane, the z-axis, which is the normal to the equatorial plane, is also going to be inclined by the same angle to the specific angular momentum vector, which is normal to the orbital plane. So the two equivalent means of measuring I are indicated in figure 4.7. Just the two equivalent ways which I have just explained. So the inclination I is the angle between the positive z-axis and h. Okay, just try to explain now. It's a positive number between 0 degrees and 180 degrees. Now we have to locate the perigee of the orbit. We know that the perigee lies at the intersection of the eccentricity vector E and the orbital path. That is, if this were the perigee, then the eccentricity vector is in that direction and it intersects with the orbital path there. So if the eccentricity vector is the one drawn there, then wherever it intersects with the orbital path is the perigee. So we need to be able to locate the perigee. So the perigee of the orbit. So the third Euler angle, small omega, the argument of the perigee is the angle between the node line vector N and the eccentricity vector E. So this is the node line vector pointing in that direction. I hope I always remember to switch between this before I start writing. So the angle between the node line vector, this is the node line vector there, and then the eccentricity vector there. The two lie in the orbital plane. So this angle there is what we are referring to now as omega, small omega. And it is the argument of the perigee, argument of the perigee. So it is positive between, it's a positive number between 0 degrees and 360 degrees. So in summary now, we have talked about the 6 orbital elements. The H, which you are very familiar with, is the specific angular momentum. The I is the inclination, which is just the angle between the orbital plane and then the equatorial plane. The big omega, that's the right ascension, just the angle between the node line and then the x axis of the equatorial plane. So the right ascension of the ascending node. E, the eccentricity, which of course you are very familiar with. Then omega, the small omega, arguments of the perigee. Then theta, the true anomaly. The angular momentum H and true anomaly are frequently replaced by the semi-major axis A and then the main anomaly capital M respectively. If we have the position vector R and velocity of a satellite in the geocentric equatorial frame, then there must be a way for us to obtain the orbital elements. So algorithm 4 gives a step-by-step procedure to get the orbital elements from the state vectors. Note that this algorithm is just the way the author of this textbook has presented his own material. There might be some other form of calculating, of course, using the same equations. There might be some other manner in which someone else, you yourself perhaps, might want to make these calculations. So, but we'll go through the textbook. I think I've also included this part already into this slide. So if I just quickly, so yeah, I've included the algorithm 4.1. So it's on the slide, but I'll be reading from the textbook while I try to explain on this other part of the screen. So when you have the state vector of course is the position vector and then the velocity vector. What one does first and foremost is to calculate for the distance. So the distance is just the square root of the magnitude of the position vector. So R is equal to square root of the dot product of the position vector with itself. So then you calculate the speed of because you have the velocity vector, you can calculate the speed. Then once you've calculated the speed, you calculate the radial velocity. The radial velocity is calculated with this expression R, the dot product of the position vector and then the velocity vector divided by the magnitude of the position vector. So if the radial velocity is greater than 0, the satellite is flying away from the perigee. And we saw all this from our discussions in AAE 313. We noted, of course, then that when the satellite, when the radial velocity of the satellite is greater than 0, when it's a positive value, that means the satellite is flying away from the perigee, and when it is a negative value, it is flying towards the perigee. So now if the one is given the position vector and then the velocity vector, of course you can get the distance and then the speed and now the radial velocity. The next thing to calculate for is the specific angular momentum, which is just the cross product of the position vector and then the velocity vector. So you do the cross product and then you get the specific angular momentum vector. Once you have the specific angular momentum vector, you calculate for the magnitude, which is the of course the magnitude of the specific angular momentum vector. That magnitude is what we had to be equal to RV perpendicular from the previous our previous discussions. So H then is the first orbital element. So what we started with the state vectors, and now we've just gotten our first orbital element. Then we can immediately calculate for the inclination of the orbit, because H, which we get by calculating from by the cross product of the position vector and then the velocity vector, it will have components in the x, y, and z direction. That means it will have some components in the x, y, and z directions. So to get the inclination of the orbit, we just have to do take the do our cos hz over h, because of course we know that the angle between h and z is the inclination. So hz is just a component of h along the z axis. So h is the magnitude. So to find this, so obviously cos I is equal to h, hz is just equal to h cos I. So it's just the component of h along the z axis. So that means cos I equals hz over h, and I then is equal to our cos hz over h. I hope I'm not writing too small already. Yeah, that should be visible now. So now we've calculated for h. With the calculation for h, we've been able to get the inclination, which is the second orbital element. You know that inclination must lie between 0 degrees and 180 degrees. So there's no quadrant ambiguity. If we calculate and we find it that it lies between 90 degrees and 180 degrees, it just means that the orbit is retrograde. It's in the negative direction. That means so for what I've drawn here, the inclination will be positive between 0 and 180 degrees. But when it is between 90 and 180 degrees, that means the satellite is rather going in that manner, going in a retrograde version, so that the ascending node, which I've drawn to the over here, will be on the other side, and then this would be the descending node. That means it's going in this manner instead. So, but when you calculate I and it is positive, then that means it is going in that manner. So now we have the specific angular momentum, the inclination. We can go on to calculate the node line vector n. Because we have the specific angular momentum vector, we can cross it with the unit vector of the equatorial XY coordinate system. So we do the cross product. And then I'm just trying to see. Yeah, let me show you what I'm looking at. So we see that this is K. The unit vector there in the z-axis is K. So we see that H, the specific angular momentum vector, and if we cross specific angular momentum vector and the unit vector in the z-axis, we are going to have a vector which will be orthogonal to their plane. So when you cross K into H, then we have a vector pointing away from the plane containing H and Z. So that's the node line vector. That means N equals K cross H. So we do the cross product and then we have the node line defined. Then we go on to calculate for the magnitude of the node line N. Then immediately we do that, we can calculate the right ascension of the node, the right ascension of the ascending node. So when you have the node line vector, you can calculate for its magnitude. When you have its magnitude, that means since it's a vector, it's going to have some component in the x direction there. That means its component there is nx, and it's just going to be equal to n cos omega, the big omega. That's the right ascension. That means you can directly find cos omega to be equal to nx over n, and then omega will be equal to r cos nx over n. So we have omega, we have I. We calculated for H, and now we are still moving on. So omega is the right ascension of the ascending node. If nx over n is greater than 0, then omega lies in either the first or the fourth quadrant. Of course, if nx over n is greater than 0, that means cos omega is positive. The cos, when the cos of an angle is positive, that means it either lies in the first or the fourth quadrant. So, but if the magnitude of nx, or sorry, if the ratio of nx to n is negative, then omega must lie in either the second or fourth quadrant. Then we have to find a way to determine exactly where it's lying. So to place omega in the proper quadrant, observe that the ascending node lies on the positive side of the vertical xz plane. So the ascending node, this ascending node lies on the right side of the positive xz plane. So yeah, this is the xz plane, and this is the positive direction. The positive direction of the xz plane, of course, is the direction of positive y. So the ascending node lies in the positive side of the xz plane. So that means we can use the information about the component of the node line vector on the y-axis to determine the sense of omega. So if ny is positive, that means, of course, omega is in the first quadrant. Or if ny is negative, that means the omega we calculate then will be in the fourth quadrant. So that is pretty straightforward. If ny is positive, then omega is in the first quadrant. If it is negative, that means ny is in that direction, then omega must be in the fourth quadrant. So to place omega in the proper quadrant, observe that the ascending node lies on the positive side of the vertical xz plane. That means omega lies between 0 and 180 degrees if ny is greater than 0, if it's positive. On the other hand, the ascending node lies on the negative side of the xz plane. Omega then is between 180 degrees and 360 degrees. If, like I've just tried to explain, if ny is negative, therefore, if ny is positive, it implies that omega is between 0 and 180 degrees, whereas if ny is negative, it implies that omega is between 180 degrees and 360 degrees. So in summary, we have equation 4.9. Then we go on to calculate the eccentricity vector. We start with equation 2.30. You can refer back to that equation. It's one of the equations we looked at when we were doing AAE 313. So the eccentricity vector is given by this expression, and then it can further be simplified through the use of the back cab rule, so that at the end of the day we have it to be couching this expression in equation 4.10. So we need, in order to calculate for the eccentricity, that is the magnitude of the eccentricity vector, we just dot the eccentricity vector by itself. So that means here we put in the expression for eccentricity vector 4.10 into this expression here, and then we have a means of calculating the eccentricity based on the parameters which we have already. We know the gravitational parameter of the Earth, we have the magnitude of the position vector, we have the speed, and then we have the radial velocity. That means we can calculate for the eccentricity. Then once we have the eccentricity, we can calculate the argument of the perigee. So the argument of the perigee is just it's just the across dot product of the node line vector and the eccentricity vector over the product of their magnitude, because the node line vector and the angle between the node line vector and the eccentricity vector is just the argument. So obviously, when we do dot product, we are looking for the component of the second vector along the line of the first vector. So this is just directly from the definition of a dot product. So, and that's the fifth orbital element, the argument of the perigee. So if n dot e is greater than 0, that is if it is positive, then the argument lies in either the first or the fourth quadrant. Same as before with omega. If n dot e is negative, then capital omega. Now with the small omega, if n dot e is less than 0, then the small omega lies in either the second or third quadrant. We need to find a way to be able to place it well as we did for the capital omega. So we need to observe that perigee lies above the equatorial plane. If the argument is between 0 and 180 degrees, then the perigee lies above the equatorial plane. If E points, so let me just switch to the computer screen here. Sorry, the camera screen. So what we are saying now is, when omega, we are counting from here, 0 degrees is there, and we are counting there. When 0 degrees less or equal to omega less or equal to 180 degrees, that means the perigee is pointing upwards. The perigee, the eccentricity vector is pointing upwards, and then it is above the equatorial plane. The eccentricity vector is pointing upwards. But if omega lies equatorial plane. So that means if we find a way, if we look at the component of E on the is it the X axis? Let me switch to the textbook. So yeah, the component of E in the Z axis. So when it's pointing up, or whether it's pointing up or pointing down, it will have some component in the Z axis. So we just need to now look at what value its components have. If Ez is positive, then we know that omega must be in the within this range between 0 and 180 degrees. If Ez is negative, then we know that it's between 180 degrees and 360 degrees. So now we have the argument of the perigee, then we can calculate for the true anomaly with this equation. The true anomaly is the sixth and the final orbital element. it also needs to be placed properly. If this dot product is greater than 0, then true anomaly lies in the first or fourth quadrant. If it is less than 0, then it lies in the second or third quadrant. You need to place it well. Note that if the satellite is flying away from perigee, then the dot product of R and V is greater or equal to 0. That will place theta in the range between 0 and 180 degrees. If the satellite is flying towards the perigee, R dot V is less than 0, and that will place the true anomaly between 180 degrees and 360 degrees. So that means we can summarize the true anomaly, the equations for the true anomaly with equation 4.138. So we can also substitute in equation 4.10, which is that one. Okay, this one for the eccentricity, we can substitute it in and have the true anomaly in terms of the scalar values of the elements that we've been able to calculate for so far. So now, with all the 6 orbital elements, the orbit of with all the 6 orbital elements already calculated for, the orbit of the satellite can appropriately be described in the 3 dimensions that it is in. So we'll look at this example as the textbook has given. I haven't put the example on the slide. No, I haven't. So, and I'm not going to put it on the slide. I think it's just okay if we go through it now, and if you also go through it on your own. So, given the state vector R equals that and then V equals that, we want to find the orbital elements H, I, omega, E, omega. There must be a way to always, I think maybe they probably call it capital omega and then small letter omega, because they are the same. One is just big of the other. So right ascension, let me call it right ascension, and then the argument using algorithm 1. You can also try to write this in MATLAB. I think there must be directions to writing it in MATLAB, and it's in appendix D8. You can follow such directions and write yours on your own. Don't just copy and the whole point of looking at it is for you to be able to know how to write your own code. So given the state vector R equals that and V equals that, we want to find the orbital elements. So the first step, of course, is to calculate for the magnitude of the position vector, and then the magnitude of the velocity vector, then get the radial velocity, and then noting that the radial velocity is a positive value, we see that the satellite is flying away from the perigee, and then we can do the cross product of the position vector and velocity vector to have the specific angular momentum vector, and then with that you get the magnitude of the specific angular momentum. Once you have the magnitude, you can do cos hz over h, you get the inclination of the orbit. And since the inclination of the orbit here is greater than 90 degrees, it means that the orbit is a retrograde orbit. And then we go on to calculate for the node line vector by doing the dot product of k and h. and then find the magnitude of the node line vector, and then with that we calculate for the right ascension of the satellite, and then we calculate for the eccentricity vector. With that, once we have the eccentricity vector, we can calculate for the magnitude of the eccentricity vector. And here, since the magnitude is equal to 0.1712, that means it is an elliptic orbit. The eccentricity lies between 0 and 1. So if the calculation had brought out a value of, let's say, 1 point something, then we would have known that it couldn't have been 1 point something anyway, because it could be. You wouldn't know which one it will be until you calculate for it anyway. So once you calculate for it, if it is equal to 0, you know it's circular. If it's between 0 and 1, you know it's elliptic in this case. And then if it is equal to 1, it's parabolic. If it is greater than 1, it's hyperbolic. Then you go on to calculate the argument of the perigee, and then we know that of course you have to choose between the first quadrant or the fourth quadrant, but we see that EZ, this one is positive. That means it's in the first quadrant. That means the argument is in the first quadrant. Then we go on to calculate for the true anomaly theta. We will not know. We also have to check the magnitude of the radial velocity to be able to place theta correctly. We already saw that the radial velocity is greater than 0. That means the satellite is flying away from the perigee. It means that theta lies between 0 and 180 degrees, and it must be this value. Because theta, of course, is read counterclockwise from the perigee. So theta in this case is equal to 20.45 degrees. Then, having found the orbital elements, we can go on to compute other parameters. The perigee and apogee radii are, we just input in the values which we've calculated for. At the perigee, true anomaly is equal to 0, and so we get that. And then at apogee, the true anomaly is equal to 180 degrees. We get that. That means with all, then we can also get the semi-major axis and then the period of the orbit. That means with the state vector, the position and the velocity vector, we have been able to define the orbit in totality. We know exactly all the orbital elements of the orbit. And this is figure 4.8, is just the plot of the orbit identified in example 4.3. So we've seen how to obtain orbital elements from the state vector. But to arrive at the state vector, given the orbital elements, it requires performing coordinate transformations, which we'll be discussing in the next video lecture. I want you to try to go over what we've discussed today, and then also go over the next thing we'll be discussing, the coordinate transformation, because it's called the coordinate transformation. We'll be talking about Euler angles, and eventually we'll be talking about the rotation of the Euler angles and all that, and it's probably going to be a bit difficult to try to explain all that over the video in this manner. Or if you've already looked at it, and then by the time I try to make some bit of explanation, it will be better to understand. So I haven't included the coordinate transformation in the slides. I'll try to do that probably in the next video lecture as well. So, but as soon as I've done that, I'll send the slides along with the video lecture. So remember to send in your comments, your feedback, and your questions. Thank you for your time.